Studying liquid solutions, and in the last class, which was yesterday, we were discussing the graph between vapor pressure and mole fraction for a solution formed by two substances. Both of them are volatile. We can call this case as non-volatile solute in volatile solvent. So A and B like are solute and solvent, and both of them are volatile, right? So we were discussing this graph. Let me just quickly explain it again. So in this graph, what we have done is, on the horizontal axis, we have plotted the mole fractions of the both components. So which means that, for example, this, if I talk about this point actually talks about only pure B, because in this case of composition, A is not present, only B is present. In this composition, only A is present and B is not present. So for example, if I take any composition here, and let's assume that in this case this is 0.3 and thereby this will be 0.7. So this is talking about a composition in which A is 30% by mole, or 0.3 as a mole fraction, and B is 70% by mole, right? Now what this graph tells us, this is the graph of the vapor pressure of A, this is the graph of vapor pressure of B, and this is the graph for total vapor pressure. So if I just figure out the values of these vapor pressure corresponding to this mole fractions, so this will be the vapor pressure of A when you have a solution. So now I have a solution of A and B in which the mole fraction of A is 0.3 and mole fraction of B is 0.7. In this scenario, the vapors created here for A and for B will be exerting vapor pressure PA, which is this, or maybe I can take it PA dash, right? Similarly, this will be the PB dash, will be PB dash, and this will be the total pressure here, PT dash. So PT dash will be equal to PA dash plus PB dash, right? So these two graphs we actually drew independently and then joined them together. This one you can see it here from the equation which we derived like this. This was the PT is equal to P naught A minus P naught B into XA or XB plus P naught A, right? So from this equation, if you see X is 0 to 1, if I just try and figure out this equation, so what I'm trying to do is I'm actually trying to find out the equation of this line, which I'm saying that it actually denotes total pressure. So how can I define the equation of this point? This will be y is equal to mx plus c, right? The c is, this is the P naught B, this will be P naught B. P naught B, 1 minus XA, right? It will be P naught B. Now, so this will be P naught B, the y-intercept. So y is equal to mx plus c. So this is the y-intercept, which is P naught B here. So this line is cutting the y-axis at P naught B, and the slope of this line, theta, tan theta will be this difference upon this value, which is P naught A minus P naught B. This is corresponding to P naught B. So P naught A minus P naught B upon 1, XA 1 minus XA 0. So this proves that this line actually belongs to the total pressure of the vapors above the liquid, right? So this graph has an advantage of for any solution which has like A and B as two volatile substances mixed together homogeneously. If you want to just find out what is the vapor pressure exerted by A vapors, what is the vapor pressure of B, and what is the total vapor pressure for any composition of A and B, you can quickly just look for that point. For example, you want like XA 0.6 and XB 0.4. So for that composition, you can find out this is the pressure exerted by B, this is the pressure exerted by A, and this is the total pressure of the solution. Now, one more thing which we can understand from this graph, for any composition of A and B, right? This horizontal line denotes what? any composition of A and B. For any composition of A and B, the total vapor pressure of the mixture lies in the range of P naught B to P naught A. It will never be more than P naught A, and it will never be less than P naught B, right? So I can say that here, that total vapor pressure of the mixture for any composition of A and B will always lie between P naught B to P naught A. The one, so here the smaller one will come, here the larger one will come, but so its value will always lie between the two. Why I'm not taking the equality sign? Because in equality situation, I'm considering this point also. If I consider this point also, I do not have a solution, I have a pure liquid. So that is why I'm not taking the equality sign. So for any even for the like 0.001 kind of concentration of XA, this will be true. Got it? So now if we come back to the theoretical question which we asked when we started this case, the case 2, that what happens when we dissolve a volatile solute in volatile solvent? Whether it will decrease the vapor pressure of the liquid or will it increase the vapor pressure of the liquid? Can you answer it now? Did you get my question? So my question is, we were curious to know that if I have a volatile solvent and I dissolve some volatile solute into it, right? So will dissolution of volatile solute in a volatile solvent increase the vapor pressure of the mixture or decrease the vapor pressure of the mixture? That's what I want to know. It will depend. It can increase as well as decrease depending upon the volatility of your original liquid. For example, if my original liquid is B in the container, this is my solvent, right? And I'm dissolving A as solute into it. And as I can see, B is less volatile. I'm dissolving what? I'm dissolving A. A is more volatile. How can I say that? The values of P naught A. P naught A is more than P naught B. So A is more volatile, B is less volatile. I'm considering B as solvent and A as solute. In such a scenario, if B will be solvent, so concentration of B will be high and A will be low, like this concept, right? In this case, the total pressure is more than the original pressure of B, which means for B, the vapor pressure has increased. But if I consider it from the perspective of A, for A, the vapor pressure has decreased. So if you're adding more volatile substance to a less volatile substance, the vapor pressure will increase with respect to the less volatile and decrease with respect to the more volatile, which means the total vapor pressure will be kind of like in between the two. Got it? And what will be the value? That will depend upon their actual values and composition you have taken. Got it? Great. Should I erase it? So as I said earlier as well, that Raoult wanted to define the mathematical equations only for those solutions in which the dependency of the equation is not on the behavior or nature of the substances. Like for example, if I say I've taken two substances, for example, methanol and water, right? Instead of methanol and water, for example, I've taken ethanol and water. Now because I've changed the substance, ideally my formula should change because the level of interaction between water and ethanol is different than the interaction between water and methanol, right? So what Raoult says that my formulas are valid, but valid only for ideal solutions. Right? Now in this case, if I want to define the ideal solution, as infinitely dilute solution, then the all that analysis which we did just now will fall apart. Why? Because if you see, now if you see, I'm considering all the possible compositions of A and B. But if I take ideal solution as infinitely dilute solution, in that case, I am limiting the concentration of one of the substances very, very low in comparison to another. But here I want to consider all the compositions possible. So in this case, I cannot take ideal solution as the infinitely dilute solution. So how do we define the ideal solution here? Certainly it's not infinitely dilute solution. Now, so what Raoult says that when you had pure liquid B, they were going into the vapor phase, forming vapors, and they were happy, right? Now you have mixed A into it, right? Because of mixing of A, the tendency of B to form vapors should change, right? And why it should change? Because A has occupied some space on the surface. This was one factor. Second factor was that A will be attracting B differently. Initially, when B was going in the vapor phase, only B atoms or molecules or particles were attracting B. Now, in this case, when B will be going into the vapor phase, A as well as B, both will be attracting. Since B's attraction will be same as previous, but now the attraction by A to B may be larger or may be weaker, because of which this behavior will be dependent on how strong this interaction is, right? Which means that nature of substance will be required to be known only when you would be considering these attractions different than these attractions. Okay, let me just take an analogy, right? For example, I'm teaching your class and I have to teach one topic, right? And you've been studying from almost 1 year, you're good friends. Now I've realized that, okay, so I have to teach a common topic to another batch also, so let's mix these two batches, and I'll teach these two batches a common topic. They are good friends, they have a nice group, but among themselves, you also have a nice group. But if I mix the two, so there are three possibilities. One is that you'll not like each other, right? Another possibility, you like each other very much more than your friends. I mean, you'll see, oh, these guys are like awesome. I mean, we'll stay with them, right? I mean, our friends are like, boring. I'll not spend time with them. Third case is that you do not feel a difference. You feel it exactly the same manner in which you feel when you are alone. Like, you are in your own group. For example, your group is group A, another group is group B. When I mix the two, you feel that nothing has changed. I mean, they are just like our friends. There's no change. I mean, I am not feeling, more attracted or less attracted or repulsive, nothing. I mean, it's just exactly the same as my group A member or as my group B member. And it's both same for both. So if that will happen, then it would not really matter to you that whether this other kids coming from group B or group C or group A, till the time your interaction with them is as same as your interaction with your own peers. You got my point? So if I'll mix A with B and intermolecular force of attraction between AA particles and intermolecular force of attraction between BB particles is almost same as that of intermolecular force of attraction between A and B particles, then what will happen? The moment you'll mix A and B, neither A nor B will feel that something has changed around me. Because if it would have changed, then the tendency to go into the vapor phase will change because of attractions between these two particles. If the attraction between these two particles is with each other is exactly same as that with each other, then in such a case, the variation in vapor pressure will only depend upon their concentration at the surface and will not depend upon the nature of substance. So Raoult defined the ideal solution as the solution when intermolecular force of attraction between A and A, intermolecular force of attraction between B and B is equivalent to intermolecular force of attraction between AB. Got it? Now let's take the second case. There are two other conditions attached to it which are linked directly to this case. One is that delta V mixing will be 0 and delta H mixing will also be 0. This is pretty obvious if you just consider this case. Now, why? Because if the intermolecular force of attraction after mixing A and B is exactly same as that of pure A and pure B, then the interparticle space will not change. Okay, let's understand it through a converse mechanism. For example, if I mix A and B, their attraction increases, as in they attract each other much strongly than they attract their own particles. In such a case, what will happen? They'll come close, their interparticle space will decrease, and thereby their volume will change, and delta V mix will not be 0. So if they do not do that, which means increased forces of attraction or decreased forces of attraction, which means if they apply almost equivalent force of attraction which they were applying their own particles, then nothing will change around them, which means their interparticle spaces will also not change around them, which means the volume will remain same and delta V mixing will be 0. Similarly, the enthalpy will not change because if the attraction would have increased, then potential energy would have decreased and some energy would have released. If the attraction would have decreased, in such a case potential energy would have increased and some energy would be required for their mixing. Now if the level of interaction is almost same, so their potential energies will not change much, and thereby their enthalpy will not change much, which means the enthalpy of mixing will also be 0. So these two are interlinked to this thing, but when we consider the ideal solution, we'll look at all the three parameters. What kind of solution do the follow this kind of condition? Ideal solution. Ideal solutions follow this kind of condition, right? How can I identify an ideal solution in general? Now, so the prime factor to understand, to identify the ideal solution is that the intermolecular force of between the two different type of particles should be equivalent to intermolecular force of attraction between these two particles with each other, right? I think instead of doing that, you should primarily consider this thing, first of all. Then you should consider the overall parameter. So first of all, I have to find those two liquids or those two substances which have similar level of intermolecular force of attraction, in which I mean same nature of intermolecular force of attraction, which means that if A has dipole-dipole, B should also have a dipole-dipole. Second thing is that the strength of attraction should be very close to strength of attraction between in the other liquid. How it can happen? Their molecular masses should not be very different from each other. They should be as close as possible. For example, benzene and toluene. Both are non-polar liquids and both of them apply dispersion forces or London forces. Their molar masses do not differ much. I think its molar mass is 72 and its molar mass is how much? 84 something? C7 H538, C7H8. 92. So it doesn't differ much, right? So because of this, they form an ideal solution. Similarly, if I take, for example, the case of chloroethane and, for example, bromoethane, methanol and ethanol, chlorobenzene and bromobenzene. Shall I erase it? Next is non-ideal solution. What if the solution is not ideal? And moreover, first of all, what all cases will be actually leading to the formation of a non-ideal solution? So if I mix the two substances A and B, both of them are volatile, and after mixing, if I realize that interparticle forces of A with its own particle and interparticle forces of B with its own particle is stronger than interparticle forces between A and B. Right? This is case one. Second is interparticle forces between A and BB is weaker than interparticle forces between A and B. So after mixing, the intermolecular force of between forces of attraction between A and B is weaker than their original case. In this case, it's stronger than their original case. So when this will happen, the solution certainly will not be ideal, and thereby it can be called as non-ideal solution. So whenever something is not fit with the ideal, we say that it is deviating from the ideal behavior, and we call such cases as deviation, right? Since these are two different kinds of deviation, we define them as positive deviation and negative deviation, right? So this is the first condition for the positive or negative deviation. Now can you just quickly tell me the other two conditions which will be linked to this? What will happen to delta V mixing? Why? Right. So because of the decreased attraction, their interparticle space will increase. So for example, if I mix the two groups and you do not like each other, so will you stay close to each other, or will you say, hey, move just two chairs on the left side, on the right side, do not sit at a distance of 1 feet from me. So basically the space will increase, which means the volume will increase, and thereby delta V mix will be greater than 0. Similarly, because the level of attraction has decreased, so potential energy will increase, and thereby enthalpy change will be positive. In same fashion here, delta V mix will be negative and delta H mix will be negative. What are the examples of the two cases? No idea? Okay. If I mix water and methanol, or for that matter any alcohol, right? In this mixing, the deviation is positive. Why is it positive? Let's just quickly understand that. If you look at the water molecule, each water molecule can form 4 hydrogen bonds around it, right? Let's assume they're just forming 2 right now, or maybe 3 right now. It can form 1 from this side as well. If I look at the methanol, it cannot form 4 hydrogen bonds, right? Thereby I can say that one thing for sure, that the interparticle force of attraction between water molecules is stronger than the interparticle forces between methanol and methanol molecule, right? 1. If I mix the two, then what will happen? If I mix the two, then the interparticle forces of attraction between the two will decrease overall. It will primarily decrease for water, less for methanol, because for methanol it would not change much, because methanol's hydrogen bonding was anyways weaker and lesser in number. But for water it will decrease significantly, which means there is an overall decrease in intermolecular force of attraction. Though initially it was hydrogen bonding, afterwards, so like I mean for H2 it was hydrogen bonding, for methanol it was hydrogen bonding, and afterwards also it is hydrogen bonding, but the strength of hydrogen bonding is weaker in comparison to the two cases, which means we can say that it's a case of positive deviation. Right? Now let's consider a case of negative deviation. So very like I mean popular example for this is chloroform and acetone. Should I erase this part? Now this is chloroform, right? And so if I consider another molecule of chloroform, as this molecule being polar, this molecule being polar, they attract each other through dipole interaction, right? This is acetone molecule. There is one more acetone molecule. Since this molecule and this molecule is also polar, they attract each other from dipole interaction. Got it? Now if I mix the two, then what will happen? If I mix the two, then in this case, there will be a strong attraction between this hydrogen and oxygen, which can be termed as hydrogen bonding. Now if you remember, so when we discussed the hydrogen bonding case, the hydrogen should be attached to a strong electronegative element, which is fluorine, oxygen, nitrogen, and can be chlorine. The element should be able to generate high amount of positive charge here. It is not connected to that. It is connected to a less electronegative element, which is slightly more electronegative than hydrogen, which is carbon. But the carbon is connected to three strong electronegative elements, which is chlorine. Because of inductive effect, it will result in high positive charge density here, and thereby we'll be able to apply the hydrogen bonding. So when we mix the two, so the two has stronger intermolecular force of attraction than the previous case, and thereby it will show the negative deviation. Right? Shall we erase it? Now let's quickly understand the graph between the two. This, the dotted graph I plotted here is the graph which was initially expected, right? Had the A and B been ideal solution, this would be the graph. But since now they're not the ideal solution, so what would be the graph of the A and B in case of positive deviation? What should be the graph? Let's just understand that. I mean, I don't know, it could be like up or it could be down. I know that the condition for positive deviation is that the intermolecular force of attraction between A and B is weaker than the intermolecular force of attraction between AA and BB, which means that when I'll mix A and B, both are experiencing weaker attraction than their original cases. Both will feel better because both of them can go into the vapor phase easily. See, I've mixed, so you were into one community which do not let you go out. There is another community of friends, like, I mean, the friends do not let each of them go out. Now, if the two are mixed, they don't care about each other much. So if one wants to go out, the other attract very weakly. If this wants to go out, this attract very weakly, which means that because of decreased attractions, either of the two particles can go easily into the vapor phase. If they can go easily into the vapor phase, they would be forming more vapors than they could originally. Which means for every case, they would be exerting more vapor pressure. That is, this graph would be higher than the expected graph. So this will be the graph for total pressure, this will be the graph for PA, this will be the graph for PB. Similarly, for negative deviation, in case of negative deviation, the intermolecular force of attraction between A and B is stronger than their original case, which means now A can not form vapors easily, B also cannot form vapor easily, so they'll be forming less number of vapors and thereby exerting less vapor pressure than they were expected to form, which means the graph would be like this. So this will be for the P total, this will be for PA, and this graph will be for PB. Noted? There's a quick query from one of the center. The query is that, like, I mean, to just re-explain the change in volume or change in enthalpy while mixing in the two cases. So before we actually move on and understand, like, I mean, whether it will decrease or increase, let's first understand what really like, I mean, what exactly do we mean by delta V mix? So delta V mixing is nothing but, so whenever we mix two substances, definitely their volume will add up. I mean, we have done it a lot in mole concept chapter or stoichiometry chapter, that when you mix two liquids, it forms, and then you find a solution, you just quickly add the two. I mean, I've taken for example, 100 ml HCl aqua solution. I've taken another 150 ml HCl aqua solution. So what will be the volume of final solution? It will be 250 ml. So we just quickly add it up. But in actuality, if I just calculate the exact volume, and if I am successfully able to calculate the exact volume with minimum error, then the volume may not be exact 250, it might be slightly higher or slightly lower than the 250. Because when you mix two liquids or two substances, they, whether their interparticle space will increase or will decrease or will remain same, will define whether their volume will increase or not. So delta V mix is volume finally, which is after mixing, minus volume initially, which is the total volume of the two liquids before mixing. For example, so this will be 250 ml, this will be 100 ml plus 150 ml. If this is 250 ml, then definitely it will be 0, which is the case for ideal solution. So in stoichiometry, by default, we were assuming all the mixing of liquids as ideal mixing, right? Not a non-ideal mixing. But what really happens if the mixing is not ideal? If the interparticle forces of attraction between the two liquid molecules is lesser or weaker than the intermolecular force of attraction between each other particle, then what would happen? They would be having more or larger interparticle space of attraction, right? For example, this is the case for AA, and this is the case for BB. So A and A particles attract each other strongly, B and B particles attract each other strongly. But now if I mix the two, mix A and B, they do not attract each other strongly, which means that the interparticle spaces between them have increased than the previous case, which will lead to the increase in volume. So that is why this will be the case. Now, similarly for negative deviation, the interparticle force of attraction between A and B is stronger than the interparticle force of attraction between their they're alike particles. So it means that the volume will decrease because of increased attraction. They'll come close to each other, and thereby the volume will decrease. In the other case, how the enthalpy can be figured out? So enthalpy of a system will decrease if the attractions in the system increases. Very similar to potential energy case. So when the attractions have decreased, the potential energy will increase and thereby enthalpy will increase. So enthalpy will increase than the previous case, which means the enthalpy change will be positive. In this case, the attractions have increased than the previous case, which means enthalpy will decrease and thereby this will be the case. I hope it's clear now. The important, so there's two things. One is that the more examples of it, you should just check more examples of positive deviation and negative deviation, and you should remember them, and you should also be able to identify these examples on your own. The second important aspect in this case is, if I look at the maximum point on this curve, for example, let's suppose this is the maximum point, and this is the composition belonging to the maximum point, right? Similarly, in this curve, let's look for the minimum point. Which curve? PT, total pressure. Let's assume this is the minimum point. This is XA and XB. Now, in case of non-ideal solution, this minima and maxima actually results in a very specific case. What is the specific case? This composition result in the formation of azeotropic mixture or azeotrope, right? This composition also forms azeotropic mixture or azeotropes. Got it? Right. Now the important aspect is not that this is the azeotropic composition and this is the azeotropic mixture. The important point is that what is azeotrope? This is something which we need to understand. What is azeotrope? Anyone? Any idea? Have you studied something like constant boiling mixture? Kind of studied, like I mean, it's mentioned in NCRT also. It's a constant boiling mixture, maximum boiling azeotrope, minimum boiling azeotrope, something like that. Okay, so what do you could understand by constant boiling mixture? Boil at same temperature? No. No. Okay. We studied distillation in our childhood, right? And in distillation, we studied that it's a technique to separate two liquids which differ in their boiling points, right? We did the distillation in some or other way in the last class. When I said that we have a liquid, we have a container. In this container, I have two liquids A and B. They're forming vapors of A as well as B. So what we were doing, we took these vapors, condensed them, made them form other vapors. We took them, condensed them, and made them into liquid, and then formed other vapors, and so on. So what really happens when you conduct the distillation for two liquids A and B, and we feel that the liquid which has low boiling point will form vapors and will separate out from the mixture. It will go into the other container, it will condense, we'll call it condensate. The liquid left here will be called as distillate, right? And that's how we separate the two liquid. It's a false story. Why it's a, no, we do that, I mean, it's not really false story, but it's like, I mean, it does not happen in one single step, because we know that even if for example, let's suppose the boiling point of B is less. If the boiling point of B is less, it means the B is forming more vapors and A is forming less vapors. If I start heating this liquid, let's suppose the boiling point of B is reached and boiling point of A is not reached, which means that more vapors of B will be forming and less vapors of A will be forming at that time. If I remove these vapors and take it to other container and condense them and form the condensate or the liquid stuff which I'll get here will not be pure B. It will all be again containing B as well as A, although the composition of B is much higher than this case. For example, here it was 40% and 60%. It will be like, I mean, B is 80% and A is 20%. If I do it again, it will increase to, for example, 10%, 90%. If I do it again, it will eventually come to a state like 100% B and 0% A. So you have to do repeated distillation usually. So when you distillate, you differentiate the two liquid for most part of it. But you do not really get the pure liquid here and pure liquid here. But when you keep on doing the repeated distillation, you eventually separate the two liquids completely, like B is completely separated and A is completely separated. Instead of doing it multiple times, you have created a hack which is called fractional distillation. So you put up a fractionating column which helps in doing all these cycles in the one single column. So instead of keeping 100 containers, it happens in 100 flask portions in the fractional distillation column. Said, well, that is not an important point. The important point is that the two liquids are separating because you are getting a different composition here. For example, it was 40% and 60% here. Now A and B here are like, for example, 20 and, for example, 80. In this case, A and B are, for example, 10 and 90 and so on. Eventually, the next condensate will be, for example, B is 100% and A is 0%, right? So they can be separated only if this composition changes. Now consider a scenario where I'm boiling a liquid A and B. One of the liquid reaches its boiling point, another does not. And in such a scenario, I'm condensing here. But what I'm getting is 40%, 60%. I'm doing it again. What I'm getting A and B as 40% and 60%. So the composition of the condensate and composition of distillate is exactly same. If I repeat this process, it will be exactly same. If I repeat this process, it will be exactly same, which means the composition is not changing, which means the liquid is boiling in such a way that it's maintaining its composition, it's not changing. If its composition is not changing, it is not possible to separate these two liquids just by boiling. So azeotrope or azeotropic mixture is such that in which if you boil this mixture, you'll not be able to separate this mixture because the whole liquid will boil at a constant temperature in such a way that it will be maintaining its composition. So the constant thing is the actually composition. So when we say constant boiling mixture, it means that it will be boiling with a constant composition. For example, if A and B here is 40%, 60%, if I start boiling and take the vapor in the other container, it will be again 40%, 60%. If I again distill it, it will be again 40%, 60%. So it will not be changing, even if I do it 1,000 times. Since it's not changing, I cannot separate such kind of liquid using distillation. I may have to separate these liquids using some other technique, but distillation will not work. So that is what azeotrope means. So azeotropic mixture forms only in case of non-ideal solution. It does not form in the case of ideal solution. First thing. Second thing, in positive deviation, it forms for the composition at which total pressure is maximum. Right? And for negative deviation, it forms at the composition for which total pressure is minimum. Right? Now, it is also related to boiling point. Though I have not talked about boiling point, but I'll just quickly give you a quick brief. I hope like you have studied in the school. So boiling point is the temperature at which vapor pressure of the liquid becomes equal to the atmospheric pressure. So a simple finding which I can use here is that higher the vapor pressure, lower the boiling point. Right? For any liquid, higher the vapor pressure. I'll talk about this in detail. I mean, just like next half an hour. Lower the boiling point. Right? So in this composition, the vapor pressure is highest for all the composition. So for this composition, the boiling point will be minimum, which so this is also called minimum boiling azeotropic mixture or minimum boiling azeotrope. Similarly, this is the minimum vapor pressure situation for this composition, and it will result in maximum boiling point. So thereby it is maximum boiling azeotropic mixture or maximum boiling azeotrope. Got it? Should I erase? So azeotropic वाला समझ में आ गया? Great. So let me just erase it. Great. Now, I'll give you an example. I mean, you would probably nitric acid is a liquid, right? At room temperature. And water is also liquid at room temperature. If I mix these two substances, they form a solution which is non-ideal, and the solution they form actually undergo the case of negative deviation. Right? This is a pretty popular example. We will also discuss this in P block. So when we produce the nitric acid, now if it undergoes the negative deviation, it will the graph would be like this, right? So if I consider the minimum point here, for example, this is the minima. For this minimum point, the composition here is 68% nitric acid and 32% water. This is by mass, right? So this is the composition which is azeotropic composition. So which this means that what really would happening, like I mean, for example, if I produce nitric acid industrially, when we produce nitric acid, the nitric acid does not come out as a pure liquid. It comes out in the form of a mixture of nitric acid and water. So we realize, oh, it's a pretty simple thing. I mean, these are two liquids, have different boiling points. What we'll do is, like I mean, we'll just distillate them. Like I mean, we'll just conduct the distillation process and we'll separate the two liquids. When we started doing the distillation, what we realize is that this solution cannot be separated further than this concentration. Because if I keep doing it, the condensate which I'll get will also have the same concentration. If I repeat it again, even if I do it through fractional distillation or any technique of distillation, I'll be again getting the same composition. So it's hard to separate nitric acid and water from this concentration using distillation as a technique, right? So what these industry guys do, I mean, they just like, I mean, pack it and ship it to the laboratory, because they know that in laboratory you do not need the pure nitric acid. You may need a concentrated nitric acid, or you would need the dilute nitric acid. So that is why this concentration of nitric acid is also called laboratory grade nitric acid, right? If for some specific situations you need pure nitric acid, so this solution, from this solution, nitric acid is separated using other techniques, for example, using dehydrating agent. Using dehydrating agent, I will remove water and I can concentrate it to 98-99% of nitric acid. Got it? But we cannot do it using distillation. Should I erase it? Now next is colligative properties. So what are colligative properties? क्या होती हैं colligative properties? No. Property depending upon mass? No. So colligative properties are properties which depend only on number of solute particles that is do not depend upon nature of solute particles. So any property which depends upon the number of solute particles and does not depend on the nature of the particles, which means that when I'm saying nature of particle, what I would be referring to is that whether this particle is small or big, whether its particle is an ion or it's a molecule or it's an atom, it doesn't really matter, right? What really matters is that how many particles do you have. If you have 2 particles, for example, this property is x. If you have 4 particles, this property will be, for example, 2x, or maybe, so it'll change only in proportion to the number of particles, and it will not change on the nature of particles, right? Such properties are called colligative properties. There are quite a lot colligative properties, like I mean, we study 4 of them, and they are, should I erase it? So we'll be studying 4 colligative properties here. One is relative lowering of vapor pressure. Second is elevation in boiling point. Third is depression in freezing point. And fourth is osmotic pressure. So these are 4 colligative properties which we'll be studying. All these properties depend upon the number of solute particles and does not depend upon the nature of solute particles, right? So these solute particles may be same, may be different, but what all I'm concerned about is how many of them are there. I'm not concerned about what kind of they are, like whether the same or different, larger or smaller, right? Now, the important thing which you should remember, and you'll not really find out, written somewhere else, the property I'm considering is actually considered for a solution where you have a non-volatile solute in volatile solvent. So the cases we consider here are actually the cases of, so we are considering a solution which consists of non-volatile solute in volatile solvent, right? So let's just quickly go through them, all 4 of them, one by one, understand their formula and the properties. Should I erase? Now, relative lowering of vapor pressure is a pretty simple case. We have kind of done it in Raoult's law. So I have, for example, A and B as liquids, and I have a solvent B, and I have a solute A, for example. This is non-volatile, and this is volatile, right? So here vapors will only be of B, not of A, right? Because A is non-volatile, right? Now, in such a case, we say that the PS is equal to P naught into mole fraction of solvent. What is PS? Vapor pressure of solution. What is P naught? Vapor pressure of pure liquid, right? Which is the pure liquid? B is the pure liquid. PS is the vapor pressure of the whole solution. Now, in this case, I want to understand relative lowering of vapor pressure. What is relative lowering of vapor pressure? Initially, the vapor pressure was P naught of this liquid. When I dissolved some amount of non-volatile solute, for example, I've taken a glass of water and I measured its vapor pressure, P naught. I dissolved some glucon D into it, and I realized that its vapor pressure has decreased to PS. I want to know what is the decrease in this vapor pressure. So it will be measured by P naught minus PS. This is called lowering of vapor pressure. Simple term, kitne se ghat gaya usko, we just like giving it a fancy name. So lowering of vapor pressure, right? Now, if I want to understand what is the percentage decrease in vapor pressure, so how will I calculate? It has decreased by this much with respect to P naught into 100. This will give me percentage decrease in vapor pressure. Now, if I do not multiply it with 100, it will give me fractional decrease in vapor pressure, right? Kitne fraction se ghata hai, right? So by what fraction it has decreased? This thing is nothing but relative lowering of vapor pressure, or I can say fractional decrease in vapor pressure. So it's just a fancy name, right? To the same basic mathematical stuff which we have studied in maybe 6th class. So P naught minus PS upon P naught is the relative lowering of vapor pressure. So let's just quickly derive an expression for it. So now I know that PS can be written as P naught into mole fraction of solvent upon P naught. So I can take the P naught as common, 1 minus mole fraction of solvent upon P naught. It'll cancel. It will become mole fraction of solute. So P naught minus PS upon P naught is equal to mole fraction of solute. This is the formula I've derived here. Now, but I want to understand that whether it's a colligative property or not. So let's do one thing. Let's take N as number of moles of solute. And capital N as number of moles of solvent. Right? Small n is the number of moles of solute, capital N is the number of moles of solvent. These are usually a standard notation kind of thing. So if I just like express it in terms of P naught upon minus Ps upon P naught is equal to small n upon small n plus capital N. This is the relation I've got, right? Now, as I know, the equation I'm applying here, that Ps is equal to P naught into mole fraction of solvent, and the case I'm considering here is a non-volatile solute in volatile solvent. This formula of Raoult's law is applicable only to ideal solution, right? What is the ideal solution in such cases? Infinitely dilute solution. If the solution is infinitely dilute, then number of moles of solute will be much lesser than the number of moles of solvent. In such a case, this value can be approximated to n. I can ignore the small n in comparison to capital N because the value is very small. Okay? So in this way, I can say that P naught minus Ps upon P naught is approximately equal to small n upon capital N. This is another relation I've got. Can I erase this? So P naught minus Ps upon P naught, relative lowering of vapor pressure, is proportional to small n. Because capital N will be fixed. For example, I've taken a glass of water, the number of moles of H2O will be fixed. Whether I add NaCl into it, whether I'll add glucose into it, its moles will not change because H2O is not going out, right? It will only be forming vapors. Let's consider that N to be remain same. So what would vary is the N, because I am adding that. So if I add less amount of salt, I'll be adding less number of moles of solute particles. If I add more amount of salt, I'll be adding more moles of solute particles, right? Now, if I'll add more salt, the decrease in vapor pressure will be large. If I add less salt, the decrease in vapor pressure will be less. So that is what it wants to prove. Now, for example, instead of adding the common salt at home, I have added glucon-D, I have added sugar, I have added salt in the same water. Again, the vapor pressure of water will decrease, but it will not decrease because you have added three different substances. It will decrease because you have added moles of sugar plus moles of salt plus moles of glucon-D, right? So it will depend merely on the number of solute particles and not on the nature of particle who all you have dissolved, right? And that's what lead to the decrease in vapor pressure. So that is why we can say that relative lowering of vapor pressure is a colligative property, because it depends only on the number of solute particles. Should I erase the right side part? Let's just quickly solve a question. Which of the following is an exact mathematical expression of Raoult's law? Which of the following is an exact mathematical expression of Raoult's law? First one, Seems like that, but should not be. See, I mean, if you just, okay, do it by the like rejection method, so this will certainly not be the answer. This will also not be the answer because it's mole fraction of solvent, which is not the case. Now, I'm confused between two. Why I'm confused between two? Because it seems very obvious that this should be the answer. But usually, what seems very obvious is not the answer. So, by reverse logic, this should be the answer. And thankfully, this is the right answer. Right? So this is wrong. Why it's wrong and this is right, why it's right, let's quickly understand that. Should I just like, I mean, quickly erase this B part, not important for us. This is the expression which we derived just now. And what I'm saying that this is not the exact mathematical expression because while deriving this expression, I've taken an approximation. Then you have got this expression. So this is not an exact mathematical expression. This is the approximated expression derived to prove that relative lowering of vapor pressure is a colligative property. It was only derived to prove that, right? But if you look at this relation, this is different from all the three. Why? All the other three? Because it has PS in the denominator, not P naught. Let's see what really happens if I take PS as the denominator. If I take PS as the denominator, this expression is not relative lowering of vapor pressure. It has no specific meaning because you're measuring the lowering of or decrease in vapor pressure with respect to the final pressure. It does not give you the percentage change. But if I just apply the formula of PS is equal to P naught into mole fraction of solvent here, it will turn out to be P naught into mole fraction of solute. I'm just skipping one step. I've taken P naught common, it will become 1 minus mole fraction of solvent, so it will become mole fraction of solute upon P naught into mole fraction of solvent. P naught will cancel. Mole fraction of solute will be moles of solute divided by total moles, and moles of solvent will be moles of solvent divided by total moles. It will get cancelled, which means it will turn out to be small n upon capital N. So P naught minus PS upon PS is small n upon capital N. In this case, I have applied a formula here and here that PS is equal to P naught into mole fraction of solvent, which is Raoult's law. And I have not taken any approximation here. So that is why this is the exact mathematical expression of Raoult's law. This is a JEE advanced question. Came in, I think, 2004, if I'm not wrong. Pretty simple, very basic, very logical. What really happened was, because I mean we have studied this equation, and this was the very obvious answer for most of the kids, and it went wrong. Okay. Apart from this question, this relation is anyways important because when you'll be solving problems, you will not take this formula as a normal formula because this formula is derived only to prove a point that this is a colligative property. Because what really happens is that when we design questions, we do not take such small things into account because we just want to understand your logic while so making you solve the numerical, and we might give you numbers in such a way that you can solve them easily, not the actual numbers. So I might be giving you a solution which is not really infinitely dilute, so that you can solve it easily. But if you consider this formula for a solution which is not really infinitely dilute, maybe dilute but not infinitely dilute, this formula will not be valid. So you should not use this formula for solving questions. you should be using formula for solving question is either this one, which is not the approximated form. But if you use this one, and I want you to calculate number of moles of one of the solute or the like, I mean, of the solute or the solvent, or maybe mass of solute or solvent, then it becomes a tedious calculation. But if you switch to this relation, there is no approximation, and since the two gets divided, so you can solve it easily because there is no addition in the denominator. Got it? Right? So I'll just give you a problem around it, so you can just note it down. So this is another important formula for the numericals. You can write down a question. What weight of glucose? You can just quickly write down a question. What weight of glucose dissolved in 100 grams of water? What weight of glucose dissolved in 100 grams of water will produce? What weight of glucose dissolved in 100 grams of water will produce the same lowering of vapor pressure, as 1 gram of urea, dissolved in 50 grams of water. As 1 gram of urea dissolved in 50 grams of water at the same temperature. So this is the question. If you could not write, I can quickly explain it. So it says that, like, I mean, you have two solutions. One is glucose aqueous solution, other is urea aqueous solution. So in glucose aqueous solution, some X gram of urea is glucose is dissolved in 100 gram of water. And urea aqueous solution, you have 1 gram of urea dissolved in 50 grams of water. What it says that the two solution shows same lowering in vapor pressure. So what should be the mass of glucose for this condition to be true? So let the mass of glucose to be X gram, and then let's quickly apply the formula. What is P naught minus PS? It's lowering of vapor pressure. So in this case, if I just apply the formula, PS can be written as P naught into mole fraction of solvent. So it will become P naught into mole fraction of solute. So this will be P naught into mole fraction of glucose, and this will be equal to P naught into mole fraction of urea. So P naught will cancel out. So mole fraction of glucose and mole fraction of urea should be same. So can we quickly calculate it? Or actually, I mentioned. Okay, so let me just quickly calculate and erase this part. I hope you have noted down. So mole fraction of glucose is equal to mole fraction of urea, right? This should be the case. This is x gram divided by what is the molar mass of glucose, 180, divided by moles of glucose plus moles of water, 100 by 18. So mass of given mass upon molar mass, given mass upon molar mass, and so on. This is 1 upon 50, 1 upon 60. Molar mass of urea is 60. 1 by 60 plus 18 by 50. So you have to solve this equation to get the value of x, right? Oh, it will be 50 by 18. Given mass of water is 50 gram, molar mass is 18. Got it? You can solve it and get the answer. I think it's pretty easy from now. Should I erase it? So this is all about relative lowering of vapor pressure. There's a one experiment, Oswald-Walker experiment, but we'll study in later. We'll just now move on to the next property, which is called elevation in boiling point. Now what is elevation in boiling point? To understand this, we'll understand first the boiling point. What is boiling point? Temperature at which vapor pressure of the liquid becomes equal to external pressure. So boiling point is the temperature at which vapor pressure of liquid equals to external pressure. Right? There's something more to it. There's one thing called normal boiling point, or in a way standard boiling point. For normal boiling point and standard boiling point, everything is same, temperature at which vapor pressure of liquid equals to atmospheric pressure, which is taken at as 1 atm. So the boiling point of water is 100 degrees Celsius, but that boiling point is a standard boiling point of water. So if I take the same H2O to anywhere in the world, like I mean if I take it to different situations, it will not boil at 100 degrees Celsius. It will boil at different temperatures. For example, if I take water in a cylinder piston system, there is a piston. I'm applying 10 atm of pressure. There is a liquid, which is water, pure H2O. It is forming vapors, and I'm heating it. If I heat this liquid, ideally it should boil at 100 degrees Celsius. But because I'm applying 10 atm pressure, the vapor pressure will not reach 10 atm at 100 degrees Celsius. It will reach 10 atm at higher temperature, so it will not boil at 100. It will boil at temperature higher than the 100, right? That is why we use pressure cooker. I'll come back to the pressure cooker case, right? Let's just quickly understand it from the graph which we studied earlier. Should I erase it? Should I erase this part as well? If you remember, we studied this thing that vapor pressure increases with temperature. Right? For example, this pressure is 1 atm. Right? So this is the vapor pressure of a liquid, for example, liquid A. So the vapor pressure of liquid A is increasing with temperature and will reach a value which is 1 atm at this temperature. So the temperature at which vapor pressure of liquid becomes equal to 1 atm will be called as its normal boiling point or standard boiling point. Right? If the external pressure is not 1 atm, it's lesser than 1 atm or more than 1 atm, the liquid will boil accordingly. For example, if I decrease the vapor pressure, for example, I go to the mountains, for example, and let's suppose somewhere in Himalayas, and at that higher height, the atmospheric pressure is not 1 atm. For example, the atmospheric pressure is 0.8 atm. Now, the vapor pressure of liquid will become equal to the atmospheric pressure at this point, which means the liquid will boil earlier than 100 degrees Celsius. That is why it's difficult to cook in hilly areas. Why is it difficult to cook in hilly areas? Because at lower temperature, the liquid will start boiling, and at boiling, liquid quickly evaporates. And it evaporates much rapidly than the normal evaporation process. So basically what will happen if, for example, if you're just, for example, cooking Maggi over there, it will not be like, soft. It will be hard to, not good to eat. So, so that case will be the case because the liquid will boil earlier. Now similarly, if you, for example, create external pressure as some higher pressure, for example, this is 1.3 atm. Now I am artificially applying higher external pressure. So there is no rule of atmospheric pressure. So I have, for example, taken a piston, some other container kind of stuff, in which I am externally applying more pressure than the usual, which is the atmospheric pressure. So in such a scenario, the vapor pressure will become equal to 1.3 atm at a higher temperature. So the boiling point will accordingly increase. Now what really pressure cooker does is, so in pressure cooker, it's a rigid container. So there is no role of atmospheric pressure, right? So the pressure itself of the pressure cooker is like high enough that it will not let the vapor pressure becomes equal to the external pressure. Because if it really happens, the pressure cooker will explode, right? So what really happens is that, so liquid starts, as in the temperature of liquid is like, going up while you're heating. It is forming vapors, vapors. And even at the higher temperature, the vapor pressure is not equal to the external pressure because external pressure is still very high, right? So the liquid in pressure cooker will not boil. But if you cook, for example, in frying pan or kadhai, and in an open state, it will start boiling very quickly, right? Now what is the problem if it starts boiling quickly or not starts boiling quickly? To understand this, let's just understand what really happens in boiling. When a liquid is not boiled, for example, your water bottle lying over the table, in this case, the water molecules from the surface are going to the vapor phase. No molecule from the bulk is going to the vapor phase because they do not have sufficient kinetic energy to overcome their intermolecular force of attraction and go to the vapor phase because they are surrounded by larger number of particles and thereby they would require more kinetic energy than usual. If I start heating the liquid and start giving these molecules sufficient kinetic energy so that they can overcome their intermolecular force of attraction, they would come into the vapor state. Even if they are in bulk, they might not have come out, but this molecule will start claiming that I am in vapor state right now, right? I mean, because see, to come into vapor state, what this molecule is required to have is that it should have high kinetic energy and should not be attracted much strongly by the other particles around it. So this particle will start announcing that by I am in vapor state. You might not be in vapor state, I am in vapor state. The moment he says so, the other liquid molecules will say, if you are in vapor state, you should not stay with us. Because we are in liquid state, then you should either go out or look for your own kind. I mean, you should not stay with us. So in such a case, what will happen is this molecule will start looking for the similar molecules. These molecules will collaborate and will form a group. This group will be surrounded by liquid molecules, and the surface which they'll create is spherical. This is nothing but a bubble, right? This bubble will start rising. If the pressure of these vapors is lower than the external pressure, this bubble A will not form. Even it forms, it will not rise. But the moment it becomes slightly more than the external pressure, this bubble will rise and will come out here. That is why if you might have observed when a liquid boils, bubble starts coming up from the bottom. And when the liquid is not boiling, for example, you have a water bottle, or you have, for example, you take a normal pan, you pour 1 glass of water into it and let it be. Do not heat the pan. The whole evaporation of the entire water may take a week, may take the whole week. You do not do anything, it just, let it evaporate on its own. It may take a week. But if you boil, the whole water will evaporate, for example, in 15 minutes or 30, or maybe like 1 hour, maximum 1 hour. I mean, if you keep on boiling, keep on boiling, keep on boiling, so the moment it hits the boiling point, it will quickly start evaporating, because the vapors are not only going from the surface but are also going from the bulk. So what really happens in boiling? So at boiling, the liquid quickly starts going into the vapor phase at a very, very fast rate. So if your boiling point reaches earlier, then the liquid will go away in the form of vapors, and it will not penetrate into the food as a part of osmosis, and your food will remain hard or uncooked. Right? That is the problem which happens in the hilly areas. To avoid that, you can use pressure cooker, because what will really happen with the pressure cooker? It will create a higher external pressure. At higher external pressure, the liquid will not boil, but still the temperature of liquid will be high. So liquid will keep on penetrating in the food, and the food will become completely cooked even before the liquid boils. If the pressure in the container increases so much that the pressure cooker should not explode, so there is a vessel which has its own weight, which can only be lifted if certain amount of pressure is created. So if you, for example, change the vessel of 2 different size of pressure cooker. So I have a, for example, small pressure cooker, and I have a large pressure cooker, and I say, okay, iska bhi to CTA, iska bhi CTA change kar dete hain. So there's high chances that small pressure cooker may explode, because that small pressure cooker will not be able to create so much of vapor pressure that it can lift the vessel and release out extra pressure, and there are like high chances of explosion. Right? So that is why you would see there is a different vessel for different sizes of pressure cooker, as per their dynamics and their strength. So that is what something really happens. You got it? Now, this is all about boiling point stuff. So as I can see, if I have, for example, so there's one more thing which we can understand here. Can I just quickly erase some part of it? Great. Let me just remove this thing. Now let's talk about the standard boiling point stuff. Remove these, right. Now I have 2 liquids, liquid A, and let's suppose I have liquid B. As I can see, liquid B is less volatile than that of A. Right? Because why? Because at same temperature, B is creating less vapors, or B is exerting less vapor pressure than A. So A is more volatile, B is less volatile. Now, this will also happen at all the other temperatures. So which means this graph will run in parallel to A and will be equal to 1 atm at this temperature. This is the boiling point of A, this will be the boiling point of B. As I can see in the graph, boiling point of B is higher than that of A. So boiling point of B is higher than that of boiling point of A. So when it does happen, when vapor pressure of B is lesser than that of A. So that is why we can say that higher the vapor pressure, lower the boiling point. Lower the vapor pressure, higher the boiling point, because it's just like so. So you can as in assume it to in terms of simple analogy. Like for example, we all have to secure 100 marks. If I've already secured 80 marks by SA1, I can easily score 20 and reach 100. But if you have scored, for example, 40 marks by SA1, you will not be able to quickly reach the 100. You would require more effort, right? So the same case, the one which is already at higher vapor pressure will reach 1 atm quickly in comparison to the one which has lower vapor pressure. We can quickly relate the same stuff to the ideal non-ideal case we talked about in vapor pressure state. Should I erase it? Now, for example, this is P naught A, this is P naught B, this is XA1, XA0, XB0, XB1. Right? I think I took different XA0, XA1. I'll take the same what I took there. So this should be P naught B, this should be P naught A, right? Now, so this is the total vapor pressure of the solution. This is the vapor pressure of A, this is the vapor pressure of B. Now I have a liquid which is an ideal solution of A and B, and there are vapors of A and B both. I want to understand at what temperature this solution will boil, right? So, or maybe like, will it boil earlier or will it boil like later than A and B? So I can compare it with, for example, this pressure is 1 atm. As I can see, the original vapor pressure of A is larger than that of B. A usually boils earlier than that of B. So as I can say, P naught A is greater than that of P naught B, I can say that boiling point of A is less than that of boiling point of B. Am I correct? Now, second thing, I also can say that the total vapor pressure of the solution lies between B and A. The total vapor pressure is more than P naught B and is always lesser than P naught A. It lies between A and B for any composition of A and B. So boiling point of this solution will always be more than boiling point of A and will always be less than the boiling point of B. Got it? Great. Now just quickly check the positive or negative deviation case here. For example, if I have a non-ideal solution, so this will be the curve for positive deviation, the blue ones, right? So this is the point where the vapor pressure of solution is maximum and thereby boiling point is minimum. The composition belonging to this case will be minimum boiling azeotrope. Correct? Now, similarly, if I have negative deviation case, this is, for example, the point of minimum. So the boiling point will be maximum here. So this composition will be maximum boiling azeotrope. Got it? So higher the vapor pressure, lower the boiling point, lower the vapor pressure, higher the boiling point. They're inversely related subjectively. Now this is all about boiling point and vapor pressure. Let's just quickly understand the colligative property thing, which we have not discussed so far. Right? Can I erase it? Go ahead. In this colligative property section, we want to understand what really happens. For example, I have pure water and I am boiling this pure water in like normal conditions, for example, open container where the atmospheric pressure is 1 atm, right? At this pressure, the liquid will boil at 100 degrees Celsius, right? Now, if I, for example, add some salt to this water, I have dissolved some NaCl in this water, 1 spoon of NaCl, and now I boil it. When I'll boil it, will it boil at 100 degrees Celsius? Will it boil at lesser than this temperature, or will it boil at higher temperature than this? This is something we want to understand. You got the objective of this particular colligative property. So let's see what really happens. Now, let me just draw the same graph, vapor pressure and temperature. Right? And let's take this thing as 1 atm. This is 1 atm pressure, right? So this is the vapor pressure of liquid. So I have a pure liquid. So vapor pressure of pure liquid increases with temperature and reaches the 1 atm at this temperature. This is the temperature I'm talking about. So this is the boiling point of the liquid. Now, if I add some non-volatile solute, any kind of non-volatile solute, in this liquid, the vapor pressure of this liquid will decrease. That is what is the Raoult's law, like Ps less than P naught. P naught is the vapor pressure of pure liquid. Ps is the vapor pressure of its solution when non-volatile solute is added to it. So vapor pressure of the solution will decrease. So it will be lower than this one. So the vapor pressure of solution will always be lesser than the liquid for any temperature, and thereby it will reach the value of 1 atm at a temperature higher than the normal boiling point. So we can say that on dissolving a non-volatile solute, the boiling point of the liquid increases. So how it becomes the solution from liquid? I've added some non-volatile solute. So on adding any non-volatile solute to a liquid, its boiling point increases. That increase is called elevation, another fancy term, right? So it's nothing but increase in boiling point. So increase in boiling point can be measured by change in boiling point, which is Tb dash minus Tb. So this is something we are interested in as a colligative property. So we say that delta Tb is a colligative property, that what is the value of increase in boiling point. This increase in boiling point will depend upon number of particles you have added to the liquid. If you have added less particles, it will increase by less quantity. If you have added more particles, it will increase by more quantity. Even if you have added two different particles, doesn't really matter. It will only depend upon the number of particles you have added. So this comes through a derivation, but derivation is not important even for the JEE Advanced. The insight is important, which I'll give you. It depends upon the molality of the solution. What is molality? Number of moles of solute present in 1 kilogram of solvent. Right? So delta Tv is proportional to small m. If we remove the proportionality constant, if we remove the proportionality, we can put up a proportionality constant, which is Kb here, which is called, what is it called? Ebullioscopic constant. It's also called molal elevation boiling point constant. This Kv can be calculated again through some other derivation. It turns out to be equal to molar mass of solvent into R gas constant Tb square delta H vaporization into 1000. So this Kv can be calculated using this formula. In this formula, this M is molar mass of solvent. R is gas constant. Tb is normal boiling point of liquid, which is a standard value. Delta H vaporization is enthalpy of vaporization. और ये enthalpy of vaporization किसका है? Liquid का. It's for the pure liquid. ठीक है? Now, so the interesting part is not this formula. Interesting part is the insight which we're going to draw from it. That is, this is molar mass of solvent, which means I'm talking about the liquid. For example, my liquid is water, and I'm dissolving some random non-volatile solute like glucon-D, sucrose, glucose, salt, blah blah, right? So I'm talking about, like, I'm concerned about the water here because that water is the solvent. So for Kb of H2O, this is molar mass of H2O. R is a constant anyways. This Tb is normal boiling point of that liquid, which is again a standard value. So for water, it will be 373 Kelvin. Enthalpy of vaporization of that pure liquid, again, that is the standard value. This is, I think, 44 kilojoules per mole. So which means that all these three values, this is constant, this is a constant, these three values depend only and only on solvent. So I can say that Kb depends on solvent only. So for example, if I have two aqueous solution, I have a glucose aqueous solution and I have a urea aqueous solution. In both the solution, if the solvent is same, which is if they are aqueous solution, it means the solvent is water. If in both the solution, if the solvent is same, then certainly I can say that the value of Kb will be same for both the cases. Their molality may be different, their delta Tb may be different, but the value of Kb will be same in the two cases, right? Just quickly note it down, we'll solve a problem around it. Done? So elevation boiling point, let's just quickly solve a problem. The problem is boiling point of a glucose aqueous solution of decimolal glucose aqueous solution is 100.051 degrees Celsius. What is the mass of Yeah, what is the mass? What is the mass of urea that should be dissolved in 1000 gram of water to obtain a solution having boiling point 100.051 degrees Celsius. Got it? So in simple terms, you have a glucose aqueous solution whose boiling point is already given to you, whose molality is also given to you. So what is asked is, what is the mass of urea that should be dissolved in 1000 gram of water to obtain a solution having boiling point of 100.051 degrees Celsius, which means same boiling point. So how would you do it? Let's just apply the equation delta TB is equal to Kb into M for glucose aqueous solution. Now delta TB is what? Normally the boiling point of water is 100 degrees Celsius, and this is 100.051. So 100.051 minus 100 is equal to Kb is not known, molality is known. Molality is decimolal, which means the molality is 0.1. Deci means 10 to the power minus 1. Deca is 10 to the power 1. Centi is 10 to the power minus 2. Milli is 10 to the power minus 3. So decimolar means the solution having molality 10 to the power minus 1 or 0.1, right? So the molality is 0.1. I'll use it. So the Kb will turn out to be 0.51. This will be minus this will be 0.051 divided by 0.1 into 10. So 0.51 will be the Kb value. Since the other solution also has the same solvent water, so I can use the value of Kb for the other equation. Now let's do it for urea. For urea, delta TB is equal to Kb into M. What is the value of delta TB for urea? We want the solution to have this as the boiling point. And what will be the original boiling point of water? 100. So which means that 100.051 minus 100. This is the elevation we want. In fact, the same elevation. The value of Kb, now we know, because the value of Kb will be same because it's also water as solvent. So it will be 0.51. I do not know the molality. This is something I'll calculate. So the molality will turn out to be 0.1 molar. So now using the formula of molality or logic of molality, I can calculate the mass of urea. How can I calculate the mass of urea? Molality is number of moles of solute dissolved in 1 kilogram of solvent or mass of solvent in kilogram. Okay, I'm erasing the question part. So molality is given is 0.1. Let the mass of urea be x gram. Its molar mass is 60, and mass of solvent in kg is 1. So it will turn out to be 6 gram. So 6 gram of urea should be dissolved so that you achieve the same elevation boiling point. Done? The next is depression in freezing point. So what is freezing point? Freezing point is the temperature at which vapor pressure of liquid equals to vapor pressure of solid. Now what it really means. For example, I have pure water, right? And I have water vapors. The two are in equilibrium. And the moment they establish the equilibrium, the pressure of these vapors will be called as vapor pressure of liquid, right? Now, let's imagine another situation. For example, in an empty container which has a vacuum, I have put an ice cube here. So this is H2O solid. Now, there are high chances that some of the H2O molecules goes to the vapor phase directly from the solid state, yeah, which means sublimation, and some of the vapor molecules comes to the solid state, which means solidification. So they will also establish an equilibrium with each other. Now the vapor pressure here will be called as vapor pressure of solid. So do you understand what is the vapor pressure of solid? For example, I take a empty container containing vacuum and I put some camphor into it. We know camphor is like, highly sublime solid. So even if I keep it at room temperature, you will find there is some vapor pressure here in the empty portion of the container, and that vapor pressure will be because of the vapors formed by the camphor, right? So that will be called as vapor pressure of solid, not vapor pressure of liquid. Now imagine a situation. What I'm doing is I'm decreasing the temperature of this water. If you might have seen that in refrigerator, in the freezing part, like where you actually freeze water and form ice cubes. If, for example, you have kept a tray to form ice cubes and it's like hot weather and just you could not wait. You wanted the ice cubes to be form quickly, as you have seen in the advertisement. When in advertisement it forms in 30 seconds, but in reality it does not, right? So you just quickly took it out. Maybe after 5 minutes you had patience for 5 minutes. So you just took it out and poured it into the glass water. You found that there are no ice cubes, so you said, okay, let it be. I'll take this whole cold water and dissolve some Ruhafza or something into it, and we'll have it, right? Now, if you see that water through a clear glass, like if you pour this water in a transparent glass tumbler, you would see that there are like very small white particles there, which we feel that might be the tray was not clean. But these white particles are nothing but these ice particles which have started forming somewhere in between that liquid. And now these are the particles which are sizable enough that you can see them. There may be those ice particles which you could not see. So for example, which means they're like some sort of H2O molecules which have decreased their temperature and have come to the state of solid. Now, at this situation, you have some H2O solid, maybe at surface, may not be at surface, but these are so small particles that you cannot really see them. So these H2O solid particles will be forming vapors, and the vapors molecules can also convert back to them, maybe to a lesser extent, maybe to a higher extent, but this will also be happening, which means that there are two equilibrium which are established to the same vapors. Case of simultaneous equilibria, which means the two equilibrium can only establish when they establish an equilibrium with each other, right? So at freezing point, what really happens is that all the equilibrium gets established and the liquid starts converting to the solid, which means this equilibrium starts establishing. You got some point, like idea about it? So at this state, when the freezing point reaches, vapor pressure of liquid becomes equal to the vapor pressure of solid. Now let's understand it from the graph. For example, this is the vapor pressure and this is the temperature. So let's assume this temperature range as the temperature range at which this liquid will freeze. For example, for water, these temperature ranges I'm talking about is the negative temperatures. At negative temperatures, only ice will be there. And if there are some vapors forming, if at all there are some vapors forming, they'll be exerting some pressure. So they'll be called as vapor pressure of solid. After a freezing point, you will observe liquid, and there will be vapor pressure of liquid. So let's assume a graph for liquid. So as I can see, there is a point at which the two becomes equal, right? At this point, so this is the temperature which will be called as freezing point, because at this temperature vapor pressure of solid becomes equal to vapor pressure of liquid. So at this temperature freezing starts, right? Got it? Now coming to the colligative property stuff. If I add some NaCl to this water and if I try to freeze it, then what will happen is, because with NaCl what really happens is that the vapor pressure will decrease. It will be lower than the pure liquid with the non-volatile solute, and thereby this will become equal to the vapor pressure of solid at a temperature lower than the original one. This is for the vapor pressure of solution. This can be taken as liquid or pure solvent. One and the same thing, right? So as I can see, a solution of non-volatile solute in this same volatile liquid, this solution will freeze at a lower temperature than the original one. For example, if water freezes at 0 degrees Celsius, so NaCl aqua solution will freeze at, for example, -4, -5, some lower temperature. So this is a decrease in freezing point, and that's what's called depression freezing point. Again, another fancy term, right? So depression simply means a decrease in freezing point. To what value it has decreased? That is delta Tf, which means Tf dash minus Tf, and what I'm interested in is the magnitude, because Tf dash will be lower than the Tf, so I have to take the difference. So either you take the mod of it or you deliberately take Tf minus Tf dash. It's one and the same thing, right? Because you want the magnitude, you're not interested in negative positive stuff. So, or you can, in formula, you can also take it as Tf minus Tf dash, because we logically know that Tf will always be greater than Tf dash. So it should turn out to be positive value, right? In such a scenario, delta Tf will be proportional to molality, and if I remove the proportionality, the constant will turn out to be Kf. Here Kf is called cryoscopic constant, and it's also called molal depression freezing point constant as the logic of it. This Kf is also related to the same formula, similar formula, molar mass of solvent are Tf square upon enthalpy of fusion into 1000, because there's a change in liquid to solid state or solid to liquid state, so that's why fusion here. Rest everything is same. Instead of boiling point, there's a freezing point. Again, Kf depends on so for any solution made by same solvent, Kf will remain same. Should I erase it? Next is osmotic pressure. Let's first understand the process called osmosis. Now I have two container. So I have one whole big container which is divided into two compartments through a semi-permeable membrane. As the name suggests, semi-permeable. It means that this membrane will let something to pass through and will not let something to pass through. So it has some half permission to let something to pass through and not let something other to pass through, right? Now, because of the semi-permeability, what will really happen in this membrane, the kind of membrane we have taken is, it will let the solvent particles to pass through and will not let the solute particles to pass through. It will not let solute particles to pass through from either side, right? Now I have two liquid and solution, on the two sides. In one side, I have pure H2O, and on the other side, I have a solution of H2O, which is another aqueous solution. Some solute is dissolved in it, which is a non-volatile solute, doesn't really matter to me. Imagine NaCl aqueous solution, imagine pure water. Now, if I do this, then will we observe some flow of liquid from one side to another side? Let's imagine this side as A and this side as B. Or will there be no movement of water from the either side? B to A, right. So liquid moves from its higher concentration to its lower concentration, a very similar phenomena as diffusion, which happens in gases. So gases move from their higher partial pressure region to their lower partial pressure region. Similarly, liquids move from their higher concentration region to their lower concentration region. Its concentration is very high. Here, in mixture, its concentration will be lesser than the pure case, definitely. So liquid will move from its higher concentration to its lower concentration, which means naturally the liquid will go here. Right? Now, so this is clear. Let me consider another case. For example, I have 0.1 molar urea aqueous solution and I have 0.01 molar urea aqueous solution. So now in both the cases, I have aqueous solution of urea. The two compartments A and B are divided using a semi-permeable membrane. To which side will we expect a flow of liquid? B to A. Why B to A? But concentration is higher here, it's lower here. Yes. So this is the constant. So there is a small confusion which usually happens. This concentration is given for solute. So this high and low concentration represent that urea is in higher concentration here and urea is in lower concentration here. If urea is in higher concentration, it means water is in relatively lower. If urea is in lower concentration, water is in relatively higher concentration. So concentration of the solvent will be kind of opposite to it. So water is in high concentration here and it's low concentration, so water will move from B to A. So liquid moves from its own higher concentration to its own lower concentration, not of the solute. Right? One more question. We have two compartments, semi-permeable membrane. Compartment A and compartment B. This contains X aqueous solution. This contains Y aqueous solution. Right? If X and Y are mixed, then some blue colored compound is formed. So in which compartment will we observe the blue color? Did you get the question? So I have a big container which has two compartments separated by a semi-permeable membrane. There is no leakage in the semi-permeable membrane. So there are two solutions. One is the solution of X. It's an aqueous solution. Another is a solution of Y, which is also an aqueous solution. So X and Y, when get mixed, they react to form some compound which is blue in color. So the moment they'll mix, they'll form blue color. So the question is, in which compartment you will see the blue color, in compartment A or in compartment B? Concentration of X is 0.01 molar. Concentration of Y is 0.001 molar. A, because liquid will move from here to here. No? Right? Correct. If I say no blue color will be formed in either of the compartment, because blue color will be formed if X and Y react, which means X and Y should get mixed, which means X and Y should be able to pass through the semi-permeable membrane. So in either ways, whether X goes from here to here or Y goes from here to here, but this SPM will not let solute particles to pass through. So it will neither let X to go from A to B or will not let Y to go from B to A. So these X and Y will never mix, because what really moves is solvent, which is water. So if water goes from here to here or goes from here to here, it doesn't really matter to them, because blue color will only form when X and Y react. So no blue color will be formed in either of the compartments. Got it? A small concept will let only solvent particles to pass through. Okay. So this is all about osmosis. Let's understand the concept of osmotic pressure. So osmotic pressure can be understood or calculated in two ways. One is so this blue thing is semi-permeable membrane. So you have a tube which is capped by a semi-permeable membrane, which is blue in color. The tube is filled with a sucrose aqueous solution. This tube is dipped in a container containing pure water. Right? This is a glass wall. This is a glass wall. The only portion where liquid can move is SPM. Right? So now what really happened? Initially the level of the two liquid in the two container is same. Right? What we realize is that because here we have pure water outside, and in the other case you have a solution of water. So the concentration of water outside is more than the concentration here. So water will start flowing in, because of which the level in the tube will rise. Because the level in the tube has increased, it will be exerting some hydrostatic pressure as per its height. After some time, this increase in level stops. I mean, it does not increase further. It just, I mean, this finds an equilibrium. So we say that this column is applying sufficient pressure which is stopping the flow of liquid from outside to inside, because still the concentration in the two region is not equal, which means the more liquid wants to flow in, but it's not been able to flow because this portion of the liquid solution is applying some hydrostatic pressure, because of which this liquid is not being able to flow. So we can calculate the tendency of osmosis or flow of osmosis in terms of osmotic pressure in like a counter way, which is that how much pressure should we apply so that osmosis stops. So this column is applying sufficient amount of hydrostatic pressure, which can be calculated as rho gh, which is sufficient to stop the osmosis. So this pressure is called osmotic pressure. This can also be calculated using a different apparatus. Now, so I have similar situation here, but with a slight difference. The difference is that one of the boundary is not rigid and it's a movable piston, and it's on the side where the constant. Oh, sorry. It's on the side of the solution having lower concentration of the liquid, because what I want to understand is this liquid will be moving from its higher concentration to its lower concentration. If more liquid will move on this side, this piston will be pushed on the right side. If I start applying some pressure here, then probably I can stop the flow of liquid from here. So the amount of pressure which I should apply so that the flow of liquid or osmosis stops will be called as osmotic pressure. Point 1. Point 2, if I start applying higher pressure than the osmotic pressure, then a reverse flow of liquid will be observed, which means water from the solution will start going to the pure water side. This process is called reverse osmosis. This is the basic principle on which most of the water purifier works these days. They're called RO water or RO purifier. So they work on this reverse osmosis concept. Osmotic pressure is denoted by pi as a symbol. This is equal to CRT by V, where V is volume of solution, C is concentration measured in molarity, R is gas constant again, and T is temperature in Kelvin. If you take the V on other side, pi is equal to CRT or N by VRT. In this case, V will not be required. Sorry. If I represent C as N by V, C is what? Molarity. So it will be what? Number of moles of solute present in 1 liter of solution, right? So V, if I take the V on this side, it will become this kind of equation where this V is volume of solution and N is number of moles of solute. Right? If you look at this equation, this is something very similar to PV is equal to nRT. So actually the whole derivation of osmotic pressure comes from the Ventoff's theory of dilute solution, which says that, as per Ventoff, in dilute solutions, the solute particles behave exactly in same fashion as gaseous molecules behave. The solute particles move in the solution. I mean, it's a very dilute solution, so their number is quite less. They keep on moving, they collide with each other, they collide with the walls of the container and with the liquid molecules. Because of their collision, they exert some pressure which is called osmotic pressure. The volume they can occupy is the volume of the solution in which they are contained, because the solute particle cannot come out. It's a non-volatile solute, right? So this is the whole volume in which it can move. So it will try and occupy whole of its volume, which is this. Its number of particles, R is gas constant, T is temperature. So if we increase the temperature of a solution, its osmotic pressure will increase. If I decrease the volume of solution but keep the mole same, which means if I increase the concentration, the osmotic pressure will increase, right? So which means that the solute particles in a liquid solution behave as same as the gaseous particles. So there's a very simple problem. The problem is that, so I have two solutions of same solute and same solvent. This is a solution of solute A and solvent B, solute A, solvent B. The two solutions are kept at same temperature, the temperature is same, but the volume of the two solutions is different, and also the osmotic pressure of the two solutions is different. Now if I mix the two solution, I'll be actually getting, for example, this is the HCl aqua solution, this is the HCl aqua solution. I'll be getting a larger HCl aqua, or maybe you take NaCl aqua solution, right? So I'll take two NaCl aqua solution, I'll be getting a larger version of NaCl aqua solution. If the osmotic pressure of the two solutions are pi 1 and pi 2, what will be the osmotic pressure of this resultant solution? See, osmotic pressure is a colligative property. It will depend upon the number of particles. Let's just see what is the value of number of particles here. So pi 1 V1 is equal to N1 RT. So N1 is pi 1 V1 upon RT. In this case, pi 2 V2 is equal to N2 RT. So N2 is equal to pi 2 V2 upon RT. Now, whatever the number of particles here and what are the number of particles here, they'll just sum up. Right? So the resultant osmotic pressure should be equal to total number of particles upon total volume, which will be actually just sum of the two, which is V1 plus V2 into RT. So I can just quickly substitute the value of N1 and N2 from here. What it will be? Or you may do it for N1 RT or N2 RT. N1 RT will be equal to pi 1 V1. N2 RT will be equal to pi 2 V2, which means this will come out to be pi 1 V1 plus pi 2 V2 upon V1 plus V2. Got it? Right? Now, let's just redesign this question a little. Did you understand this question? You got it? This solute here. A and C both are non-volatile solute, and B is a volatile, as it was previously, just to mention it more specifically. So what I've done is I have actually changed the solute in the other container. Now what will be the resultant osmotic pressure? It will be same. Because osmotic pressure being a colligative property, it does not depend upon the nature of particle, it depends upon the number of particles. So it doesn't really matter whether now I have particles of A or I have particles of C. What really matters is how many particles do I have, right? So the same formula can be applied even if these two particles are different. Now, what will change if A and C can react with each other? For example, I have taken NaCl aqueous solution here and I have taken silver nitrate aqueous solution here. The moment I'll mix the two, AgCl will be formed and it will precipitate out. It will not be a part of the solution, right? So if the two can react, then what will change is number of particles finally left in the solution. So if the two different particles you have taken or solute you have taken, if the two can react with each other, then all you have to do is just take care of a simple case that after reaction, what is the total number of solute particles left finally? If they are non-reacting, then you'll just add them up algebraically. If they're reacting, then you'll just apply mole concept or stoichiometry and you'll find what is the number of moles of the final solute left. And that's how you can calculate it. Same logic, great. Now last concept is so I have two solutions A and B. Let's assume both of them are aqueous solution but contains different solute. Right? If I say osmotic pressure of A and B are equal, their concentrations are in such a way that the osmotic pressure coming out as a value at whatever same temperature or different temperature, usually they are same temperature, is equal, then in that case I can say that A and B are isotonic. So what are isotonic solutions? The solutions having same osmotic pressure. If the osmotic pressure of the two are not equal, and let's consider a case where osmotic pressure of A is more than B. It could be other way around. The one which has higher osmotic pressure is called hypertonic. And the one which has lower osmotic pressure is called hypotonic. Solution having higher osmotic pressure. Solution having lower osmotic pressure. So this is used in biology when we study the red blood cell. So the outer covering of the red blood cell is a semi-permeable membrane. If I keep it in a container which is filled with (1% NaCl aqua solution), then what will happen? It will swell or shrink. To know this, you need to know that a cell contains 0.9% NaCl aqua solution. This is the concentration inside and this is the concentration outside. So which way the flow will happen? Will this cell swell or shrink? It will shrink. Right? And if this is 0.1%, it will swell. Right? If it's 0.1%, then it is hypotonic in comparison to internal solution. If it is 1%, then it is hypertonic. So we just use the same logic. If we put red blood cell in a hypertonic solution, it will shrink. If we put red blood cell in a hypotonic solution, it will swell. That's how we define the hypertonic. Got it? Now, should I erase it? As we said, these all colligative properties depend upon number of solute particles. It does not depend upon the nature of solute particles. Now there are chances that, for example, I have dissolved NaCl in water. I have taken 1 mole of NaCl and I have dissolved it in, for example, 1 liter of water. So what I'll say that the concentration of NaCl is 1 molar, right? But I know that when I dissolved NaCl in water, it actually dissociates into Na plus ions and Cl minus ions. So now in water I do not have 1 mole of particle, I actually have 1 mole of Na plus ions and I have 1 mole of Cl minus ions, which means I have 2 moles of particles. And for my colligative property, it does not really matter whether they are small particles, large particle, whether they are ions, neutral molecules or atoms. What all matters is the number of particles. So because I'll be estimating the values as per the 1 mole, but I'll be getting result as per the experiment on the basis of 2 moles. So when your solute particles dissociate, it increases the number of particles and thereby changes the colligative property value in the experiment in comparison to the value you calculate using formula, right? Similarly, if you have some particle, for example, acetic acid, which is dissolved in benzene, it has a tendency to dimerize. This can also called as association. So when solute particles associate, they start clubbing together and form smaller particles, larger particles. So the number of particles will decrease and thereby the colligative property value again will be lower than the expected value. So in case of association and dissociation of the solute particles, the value of colligative property or the actual value of colligative property will not be same what you will calculate on paper using the formula. So how to take care of that? That comes under the category called Vent-Off factor. This is the last topic we'll study in the next class. We'll quickly finish it and then move on to the next chapter. So just before you come to the next class, just read about it, Vent-Off factor. And we'll solve some more problems around the chapter. This is it for today. Thank you.